All right, so class 71, we looked at the Doppler effect. So the do now is just kind of going over some topics we've seen before or some ideas that we're going to use. So if a wave does not change medium, its speed remains the same. I'll just write RTS for that. In a given medium, if the wavelength of the wave increases, the frequency must decrease. In a given medium, if the wavelength of the wave decreases, the frequency must increase. I'll redo that. So we watched some videos, we saw a simulation. You can check those out. But what we ended up seeing was that as an object emitting noise approaches you, you hear a higher frequency because the wavelength becomes shorter. As it goes away from you, you hear a lower frequency because the wavelength becomes longer. Now, let's say you switch things up. Instead of the object emitting noise approaching you, you approach the object that's emitting noise and it's not moving. So you approach a stationary object that is emitting sound, you hear a higher frequency. So you're still approaching, so you still hear a higher frequency. The second part here really isn't that accurate. It's more not necessarily due to the fact that the waves get shorter, but actually more due to the fact that you're moving towards the waves and you're hitting them faster. So that second part isn't really that accurate. You could write shorter, but you're better off just leaving it with the first part of that sentence. And when you go away from a stationary object, so the object emitting sound, let's say it's a car leaning on its horn, is emitting sound, it's just parked there. And as you move away from it, you hear a lower frequency. And again, it's not necessarily because the wavelengths are becoming longer. It's actually because since you're moving away from it, the wavelengths are hitting you less frequently. So to sum up the Doppler effect, basically, as objects approach, and it doesn't matter who's moving, frequency goes up. As objects go away from each other, and again, it doesn't matter who's moving, frequency goes down. That's the big takeaway. And there has to be motion. So if you're stationary, or if both objects are stationary, there's no change in frequency. If you move a little closer and then stop and nobody's moving, the frequency doesn't change either. It's only while one or both of the objects are moving. So we checked out this video that had to do with sonic booms, and we related it to the simulation we had seen earlier. So in that simulation, we set the speed to the speed of sound, which was 1 in that simulation. And we said, what do you notice about the frequency observed as the source travels at the speed of sound approaching the observer? Explain why this makes sense. So the frequency observed in that case was actually equal to question mark, question mark. Why was that? Because the sound hadn't gotten there yet. If you're traveling at the speed of sound, or if let's say a plane is traveling at the speed of sound, you're not going to hear it until it reaches you, or until the Mach cone, that's not really something that we need to know for this class, reaches you, all right? So what we can say here is that the sound travels with the object emitting it. So the sound reaches at the same time the object does, not before. And what do you notice about the wave crests when the source travels at the speed of sound? So what you notice was all the wave crests lined up or stacked on top of each other. So if you think about a lot of waves all lining up together, you get this huge constructive interference. The result is one giant sound wave, which we interpret as the sonic boom. And one thing that the guy in the video brought up, which is a really good point, is that the sonic boom doesn't just happen once. Okay, anytime that sound first reaches an observer, the sound emitted from, like, let's say, an airplane going over the speed of sound, anytime the sound from that airplane reaches the observer, they hear a sonic boom. So it's constantly going. It's not like a one-time event that happens. Let's say a plane is flying over a beach. Everyone on the beach is going to hear the sonic boom at a different time of when that sound reaches them. So here are a couple of practice questions. The first one says, the horn of a moving vehicle produces a sound of constant frequency. Two stationary observers at A and C and the vehicle's driver B, position as represented in the diagram below, hear the sound of the horn. Compared to the frequency of the sound of the horn heard by the driver B, the frequency heard by A is, let's kind of draw this out. So what's happening here is, sound waves are emitted, they get bunched up, going forward and spread out behind it. So the person at A is going to hear a lower frequency. The person over here at C is going to hear a higher frequency, and the person at B is going to hear the real or the true frequency. So the person at A is going to hear a lower frequency, so we eliminate choices 3 and 4. The person at C is going to hear a higher one, so it's choice 2. This next one, let's see, a horn of a car produces a sound of constant frequency. The car traveling at constant speed approaches, passes, and then moves away from a stationary observer. Which graph best represents the frequency of this sound wave detected by the observer during the time interval in which the car approaches, passes, and moves away? So let's see, on the approach, remember, as two objects get closer together, we hear a higher frequency, so high frequency. As it passes, they're going to hear the real frequency, or the emitted frequency, you can say. And as it moves away, you're going to hear a lower frequency. So which one shows that? Well, there's actually two options you can start with. Some people said choice 2 and some people said choice 3. We can eliminate 1 and 4 because those two say that the frequency gets higher as time goes on. But remember, it's approaching first. Now, I just want to talk about why it's choice 3 and not choice 2. As we approach, as long as it's at a constant velocity, that higher frequency is going to be a constant higher frequency. It's not going to gradually get lower. So this is on the approach. Then as we pass it, it's kind of like a step function now. As we pass it, the frequency is all of a sudden lower, and it's a constant lower frequency. So this just moves away. This point here in the middle, that's where it's passing.